is metabolized to give us piroxicam, which indeed is our active drug. Have I gotten any answer? Umenyamaza kabisa. Have you given me the answer? I'd asked you a simple question. Oh, can't see any response. Any response? I had asked. I just went to show you the difference. I had asked you, if you look at the structure of piroxicam compared to piroxicam, do you expect any differences in terms of reactivity or in terms of pharmacological activity, whether positive or negative, when you compare piroxicam and isoxicam, and why? Class, any answers? Any answers? Would you expect there to be any differences in the reactivities of isoxicam and or in their pharmacological activity or any other effects, and why? Took so long to answer. Sometimes it's like you go to the books. I hope you don't Google when I ask you simple questions. Let's get an answer quickly. I would want us to move on quickly. Time moves so fast. Some answers quickly, class, students. Some answers, please. Many answers. As many as you try to answer these questions. Because by now, we have mentioned so many of these rings. Remember, like when we were looking at the thiazole ring. This is a thiazole ring. And we did mention when you introduce a thiazole ring, you increase water solubility. You increase polarity. When you were looking at the antibiotics, we said every time you introduce a thiazole ring, you increase the polarity. But here we are only talking about that you require a heterocyclic ring. You see, even in piroxicam, this is not a benzene. It is a pyridyl ring. So we are going to look at that. I'm just at least waiting for one or two of your answers. They are taking long. Wow. Yes, Kadia, thank you, Kadia, for trying. Is more active than piroxicam because it also has a high electron withdrawing capacity than pyridine. Correct. It's a very good. It's a very good answer. Because if you look, because of the time, and some of you do not want to try even and answer, and that was very good, Kadia, because it's a very good argument that you see. If you look at this ring, there is isoxazole ring. This ring has oxygen and nitrogen. Oxygen and nitrogen have the highest electronegativity compared when you have added oxygen. This oxygen increases electronegativity, the pool of electrons. When it increases the pool of electrons, it increases the rate at which your ionization or your formation of your ionized ion. Remember, we did mention we require an ion. It's called the enolate ion. And because of that, therefore, you will also find, so this could have higher activity. But the worst is that because of the fact that it will make this drug more acidic, then it's also expected to be this drug to be more acidic. I'm not saying the acidity, the higher acidity is what is resulting to its higher activity. What is resulting in its higher activity is its ability to form the enolate ion, or to undergo the ketoenolatomerism, to form the anion. Remember, we do require the anion to bind the receptor. But because of the high electronegativity of this group, it means this drug will also have much higher acidity, and in having much higher acidity, it will of course also have much more gastric irritation. For these drugs, it was found that the extent of acidity really did not affect activity, but of course you'd expect that the formation of the enolate ion is very, very key. The stabilization of the enolate ion. Remember, once you form, we are going to look at it, and once you form the enolate ion through the ketoenolatomerism, then it requires stabilization. So indeed, we do expect isoxicam, we expect it to have more acidity. You are expected to have higher reactivity because of the rate of formation of the enolate ion, which is responsible for binding of the receptor. So we are looking at, again, this drug. Again, let us always start with the numbering. When you're discussing the SAR, you must start with the numbering. The sulfur carries position 1, position 2, position 3, 4, 5, 6, 7, 8. Then these ones could carry the primes. So once you look at this, you can, and all of them, the structures we have looked at, all of them are characterized by the 4-hydroxybenzothiazine heterocycle. 4 because 4-hydroxy benzo, that's a benzothiazine. So 4-hydroxybenzothiazine heterocyclic, and that they must have 4 activity. The acidity of the oxycarbon is attributed to the 4-hydroxyl group, with the enolate anion being stabilized by the intramolecular hydrogen bonding to the amide nitrogen NH group. We are going to look at, we are going to form look at this, and we are going to look at it in a minute. I said here you have a bond here. That coming in here, if it comes in here, you form a double bond here. You cannot retain this double bond. This double bond moves here. If it moves there, this oxygen must move out. So when, and this, you can draw a dotted line there. So when you have this carrying O minus and this carrying a double bond, and that keeps changing, that's why sometimes you just put a dotted line. When you have this carrying an O minus, that is what we are calling the enolate ion. And that enolate ion, remember, when you have an oxygen minus, it can form hydrogen bonds with nitrogen. So that's why we are saying any oxygen, when you have oxygen, it can form hydrogen bonds with, of course, another hydrogen, which is attached to a nitrogen. If you look at this hydrogen is attached to a nitrogen. Remember, hydrogen bonds are formed by hydrogens that are attached to nitrogens, hydrogens that are attached to oxygen, or hydrogens that are attached to fluorine. They will form hydrogen bonds. So this hydrogen, because it will be delta positive due to the pull of this electron, it can form a hydrogen bond between the oxygen and the hydrogen. Remember, when you form a bond, you stabilize. So that molecule, so the enolate ion will be further stabilized by formation of hydrogen bonds between that oxygen and the hydrogen or the electron deficient hydrogen of the carboxyamide. Also, the presence of the carboxyamide substituent at the 3 position, that is the 3 position, you can see that's where the carboxymidase of the benzothiazine ring contributes towards acidity by stabilizing the negative during ionization through resonance. Remember, this coming in here, that coming in there, that is what we call resonance. So this enolate ion is stabilized through resonance, and therefore it does have stability, because when it comes as O minus, it can go back, and then you go back to the original situation. Then it comes back. That's a stabilization, that there is a distribution of electrons between the oxygen and the hydroxyl group, and that stabilization allows for the stability of the enolate ion, and the fact that this compound can exist as the anion, and the anion is what we are calling the enolate ion, and we require that anion for activity. Although these compounds are acidic, they are somewhat less acidic than the carboxylic acid non-steroidal anti-inflammatories, but they are primarily ionized at physiological pH. They are less acidic than the carboxylic non-steroidal anti-inflammatory drugs, but what is of importance is the fact that they are ionized at physiological pH, and therefore they do have the acidic nature. And the acidic nature, all we require it for, as I said earlier, is the formation of the anion, because you require an anion to bind through electrostatic bonds or ionic bonds to the cation, which is within the COX enzyme. Acidity is required for COX inhibitory activity. That statement is loaded, and you know it, because that acidity, it is not the acidity per se, it is because when you have the acidity, then you do have an anion, and that generated an anion is able to bind the cationic site, which is found within the COX enzyme. The long half-life of this agent is due to, in part, the lack of the carboxylic acid functionality, which can be glucuronidated in all the others. And therefore, you find most of these drugs, including piroxicam, meloxicam, usually you give them once daily. Unlike The other ones we have looked at, the aspirins, the indomethacins, more often than not, the indomethacins, the aspirins, you give them apart from the diclofenac, which we said you make a retard formulation, but most of the others, you have to give them with a higher frequency because of the high rate of metabolism through glucuronidation because of the presence of the carboxylic group. So again, it's the same thing here. It's just a repeat within the series. The 4-hydroxy-1,2-benzothiazine carboxamide was observed when R1 was a methyl group, so that we are still going further. So those were the characteristics we are mentioning. We are looking at the SARs, and we are saying when R1, so this is a general structure, an R there and an R1, general structure of the oxycams. And all we are saying is that it was found that when R1, that is for the benzothiazine carboxamide, because we have different types of these drugs, but for the benzothiazine carboxamide, when R1 was a methyl group, then the resultant molecules had maximum activity. And that is why, if you look at the structures of the oxycams, this R1 is a methyl group. The carboxamide substituent R generally is an RL or heteroaryl substituent because alkyl substituents are less active. So R can be an RL or heteroaryl. And indeed, we'll find out that indeed, if you look at almost all of them, a heteroaryl was found to be more active than the RL, because the heteroaryl further brought about stabilization, further stabilization by resonance. So although we are saying we can have R as an aromatic, R is like a phenyl group, a heteroaryl was most appropriate. And if you look at the structure of all your drugs, if we go back and we look at the structure of all the drugs that we have mentioned, you can see that this R1 is really not an aromatic group. It is a heteroaryl. That's a heteroaryl even for peroxicam. And we are saying it's because this nitrogen or the heteroatoms found within the heterocyclic group was as R1 were able also to stabilize further the enolate which was formed and therefore giving better activity. Oxycam are acidic compounds, yet when you have already said the N-heterocyclic carboxamide generally are more acidic than the corresponding N-aryl carboxamides. They are more acidic, they are more stable. More acidic, as the acidity of these drugs will depend on the stability of the ionized base or conjugate molecule that is formed. If the conjugate molecule is stabilized by resonance, it's more stable, and therefore that drug will have better activity. This enhanced acidity was attributed to stabilization of the enolate anion by the heteroatom, as illustrated as you're going to look for peroxicam. So I only want you to get there what we are talking about, the principle. We are saying, number one, the hydroxyl group, or the fact that these drugs do have an area that allows for keto-inototomerism. That's the starting point. That they can undergo keto-inototomerism and therefore lose a proton and create a negative anion. And in creating that negative anion, the second point is the structure that we have is able to stabilize. It is able, this kind of structure we have in itself is able to stabilize the anion that is formed. One, through hydrogen bonds, through the hydrogen of the carboxamide. Number two, it is also able to stabilize because the R1 or the extra second ring has a heteroatom, and therefore that heteroatom, remember the nitrogen, the oxygen, even the sulfur, do have lone pairs of electrons, and those lone pairs of electrons can participate in the delocalized electrons of the double bond and therefore bring about stabilization. So they can bring about stabilization through resonance and hence stabilize the enolate ion, and you require that enolate ion. That ion is the one that binds the COX enzyme, the cationic site of the COX enzyme. So that is very important for us to understand. So now we see how that happens. And here we have our peroxicam. So the peroxicam, the first thing that is happening here, remember here there's a double bond, moves in, and you get a double bond there. This moves out, it comes here, then this moves out. That's why we are saying we are drawing a dotted line along these atoms, because at any one time, any of them can carry this negative charge. So these electrons are all being shared They are all being shared amongst this oxygen and that oxygen. So that is why we draw it that way. So that can carry a negative charge, and also this oxygen can carry a negative charge. So that's why we are saying, so this can come in to carry a double bond, and this also can carry a negative charge. So because of that change, they can keep changing. We give them, both of them having a negative, and the electrons are shared along or amongst all these electrons. And because of that sharing of these electrons, that's what we are saying, stabilization. This negative is what is giving us the delta negative, is what we're calling the enolitone. So that sharing of those electrons through resonance is what is stabilizing this molecule. Of course, this molecule has already lost a proton. Then again, we are saying this nitrogen, like in piroxicam, has lone pairs of electrons, and therefore this nitrogen, the lone pairs of electrons, can move in. So those electrons can move in. So we have this lone pair of electrons here moving in, and if they move in, this carbon would be overloaded. So this double bond, which originally there, will move out to here, and this, of course, nitrogen will be overloaded. That hydrogen now can shift to come here. So when that happens, so this is the next now, whereby we are saying the lone pairs of electrons here can participate in stabilization of, again, further the enolitone, and in that further stabilization, that molecule, so that anion, is highly stable, and therefore very, very stable, and therefore available, very stable and available to bind the COX enzyme. So this is the same thing, piroxicam there, and of course it's good that here we have put it has lost a hydrogen, and in losing that hydrogen, we are saying this is the other one where we are not drawing. So we are forming that, and then after forming this negative can keep shifting, and that is now where we put the line, and the negative is between the whole of this. The negative charge is being shared amongst all these atoms, that oxygen and that oxygen, and therefore a lot of stabilization. And then from there, we are saying, of course, the lone pair of electrons can come in here, and again, we have further stabilization of the enolitone through resonance. So that anion, very, very stable and highly available to react or to bind the COX enzyme. Piroxicam, it is the first example within the oxycam. It's a prototype. It is an effective inhibitor of arachidonic acid. The greatest incidence of side effects is not from GIT disturbance. Meloxicam, if you look at the difference between meloxicam, is where we did mention meloxicam has the thiazole ring, and it has a methyl substituent, meloxicam. You have the meloxicam here, thiazole ring, and it has a methyl substituent. And what was found is that after you do this replacement of the pyridine ring with a methyl thiazole ring, it was found the resultant drug, which is meloxicam, has higher preference. It has higher preference for COX-2 than COX-1. It is not a selective, let us note it. It is not a selective COX-1. It's not a selective COX-2 inhibitor, but it has higher tendency to bind COX-2 than COX-1. It will still bind COX-1, but higher tendency to bind COX-2 than COX-1, and therefore meloxicam has slightly lower gastric irritation than piroxicam, and of course also than the other non-steroidal, non-selective, non-steroidal anti-inflammatories. And if you look at the mechanism of action, remember I mentioned three. I mentioned the first one where we have irreversible inhibition by acetylsalicylic acid through the normal inhibition and through acetylation. Then I mentioned whereby you can have preferential inhibition of COX-2, and I gave an example of meloxicam. This is what we are talking about. And then, of course, I said the competitive, the reversible competitive inhibition, and that, of course, is of most of the other drugs, including for the other drugs, whereby they do not acetylate the other drugs, like the indomethacins, what have you. They will do competitive inhibition where they have no acetylation. But aspirin, in addition to competitive inhibition, also acetylate it. Meloxicam has higher preference for COX-2 than for COX-1, and therefore bringing us lesser toxicity compared to piroxicam and the other non-steroidal. But it is not a selective. It is not a selective COX-2 inhibitor. The selective COX-2 inhibitors that we'll be able to look at are celecoxib, which basically go for COX-2 and not for COX-1. So that is piroxicam as an example. And then we are saying piroxicam is selective for, not really, it's selective, it's more selective, a preferential selectivity, but it's not completely selective for COX-2, but we say it has higher selectivity for COX-2 than piroxicam, but it's not a total non-selective inhibitor. The general structure activity relationships of the oxycams, and we are saying primary carboxyamides are more potent than the secondary corresponding derivatives. Why? We have just said, if you have a primary carboxyamide, it also further stabilizes the enolate ion through hydrogen bonds. If you have a secondary carboxyamide, it will not have a hydrogen. In place of the hydrogen, will have a larger group. That stabilization will not be there. So we are saying primary carboxyamides are more potent. And if you look at all those drugs, they're actually primary carboxyamides. They're derivative because the NO-NH bond is available to enhance the stabilization of the enolate for the secondary. And that, again, we have discussed. When the aryl group is O substitute or is ortho substituted, variable results were obtained, whereas meta-substituted derivatives are generally more potent than the corresponding isomer, for example, meroxicam. What we are saying, when you look at the group, where are you going? All we are saying is that when you look at these drugs, if you look at this drug, the meloxicam, we are considered this is ortho meta. So this is a meta substituent. It gave a much higher activity. When it was done ortho gave different activities depending on the group. And I think we did mention that when we were also mentioning these drugs that we're calling the anthranilic acid derivatives or the phenamides. They also had that effect. But we are saying that, like in when you have a meta substituent, you have maximum activity of a meta para, but para substitution was found to be lesser than the other. So that is all we are saying. Look at that. When the aryl group is also substituted, variable results were obtained, whereas meta-substituted derivatives are generally more potent than the corresponding para isomers. So, and we have an example of meroxicam. In the aryl series, if you have aryl series, again, maximum activity is obtained with a metachloro group, but we do not have any example of a drug which has a total aryl group. All of them are heterocyclic derivatives. No direct correlations were observed between acidity and activity, partition coefficient, electronic or spatial properties in this series. So all we have said is that you can have, so we are saying the heteroaryl group on the carboxyamide side chain is very important. The heteroaryl group on the carboxyamide side chain is also very important. It will give you different activities depending on whether it's substituted or not. It will give you different activities depending on its own nature. Is it an alkyl group? Is it a heteroaryl group? Is it an aryl group? So that substituent on the carboxyamide group side chain, very important. So two major differences, however, observed when R is a heteroaryl rather than aryl. In fact, we do not have any drug, as I have said, where you have the aryl. Aryl is a phenyl ring. pKa values generally are 2 or 4 units lower. Anti-inflammatory activity increased as much as 7-fold. And we have said the anti-inflammatory activity is not really related to the acidity. It is related to the fact that when you add an heteroaryl group with a heteroatom, that heteroatom further stabilizes the enolate ion, and therefore giving these drugs better reactivity. The greatest activities associated with either a pyridyl group, and the pyridyl, of course, where you have piroxicam, and we have said why. The 2-thiazole group, like in sudoxicam and meloxicam, they have the azolyl group, or the thiazole ring. Then you have, of course, the isoxazoline ring found in isoxicam. But we have also noted that isoxicam has been withdrawn from the market following several reports of skin reactions, but the others, I believe, a drug like meloxicam quite common, and of course piroxicam very feodine, and very common in our markets, even in our Kenyan markets. The heteroaryl carboxamide also possess longer plasma half-lives, providing an improvement in dosing scheduling regimens. That I had already said that you find that these drugs, they are more often than not given as a once daily dosage. Of course, once you have such a regimen, especially for you have that such a regimen, of course you have improved patient compliance, because it is easier to once. Like if I'm coming to class, I take it in the morning. I will not bother. Very busy, even as a student, you will not bother during the day, and then again you take it after every 24 hours. So you're thinking of, even if it's after every 12 hours, that is BD or OD. You will either think of taking it in the evening or taking it the following day, but without its activity being influenced or going down, and without it interfering, because most of the people, especially these days with the funny diseases, that people don't want to be seen taking drugs. So it's like there's a stigmatization. So if you can take the drug in the safety of your cube, of your house, you feel much better. So once you take it once day, you take in the morning before you leave, you take in the evening, or you take tomorrow, or whatever, if it's depending on the dosage, then of course there is better patient compliance. Metabolism, due to the primary difference in their structures, of course, these drugs will be metabolized. Again, metabolism for all drugs, as we've already seen, is structure dependent. Piroxicam undergoes pyridine ring oxidation followed by glucuronidation, and a small fraction also undergoes hydrolysis. Meloxicam undergoes slow hydrolysis of the benzylic methyl group of the thiazole chain. So again, we have said severally that for most of the drugs, metabolism for sure is structure dependent. So here we have our piroxicam. I've only mentioned the two, some of the most important. So you have the piroxicam. Because of this ring, you can see this hydroxyl group there. This hydroxyl group can increase the electron density of this ring through resonance, and increasing that increases the metabolism of that ring through oxidative hydroxylation, and you can get that group. The most of the positions are usually, if it is here, ortho or positions. That's why we have put it. It's quite a number of those positions can be hydroxylated. So that is one of the metabolites. Then the piroxicam, it can give us the major metabolite. That's happened in this one. And this is in dogs. We are not interested in dogs. So the piroxicam in humans is where we are interested in the metabolite, whereby again this nitrogen this nitrogen here and that nitrogen can interfere with the metabolism, and again, because of this nitrogen, this is giving us the major metabolite, which is a para-hydroxy metabolite. And of course, also that nitrogen further increases the electron density, giving us the para-metabolite, and that is a major metabolite in human beings. So that is the only change that has occurred there. So you can either have oxidative hydroxylation of that ring, but oxidative hydroxylation of the pyridine ring is higher, and that's a major metabolite in humans. And of course, also it can also undergo other metabolic processes, whereby it gets a cleavage here. You get a cleavage here, cleavage there, giving us that goes on its own. And you get, once you get a cleavage there, it's like a hydrolysis of the amide bond. In fact, this is an amide bond. So you can get, amide bonds are a little bit more more stable, but it can still undergo that cleavage by amidases to give us that carboxylic derivative, and that carboxylic derivative can undergo again further metabolic processes, or quite several metabolic steps, and give us that product there where you have no carboxylic group. And finally, it can give us saccharin, which is a very minor metabolic product. I think, I don't know whether you have that metabolism of piroxicam. I think the one I've given you is only the major one. I've given it up to this. I've given up to this. I've not given saccharin. I've given that you find in your handout, but you can, of course, from your handout, you can see which is the major. And of course, once you have the hydroxyl group, again, you can get glucuronic conjugation, and you can, even in your handout, you can mention which are the major ones and which are the major ones. And we have said the major ones, as I've said, we are not interested really in the dogs, we're interested in the human being. It is the hydroxylated pyridyl metabolite, which is a major metabolite. So that is piroxicam. Again,